mTeSR1 was the first feeder-free media for maintaining pluripotent stem cells. This was first described in Nature in January 2006 in the Jamie Thompson lab in Wisconsin by a researcher named Tennille Ludwig. TESR is Tennille's special recipe. mTeSR1 was a very expensive medium. It contained human recombinant proteins, human serum albumin, and at the time, in 2006, when this was being developed, this was an extremely high-cost way of creating media. So immediately, that was proof of principle. They wanted to try to bring the cost down, and the two things that they did was to swap HSA out for BSA, and to create a very efficient way, a low-cost way, of generating BFGF, and that was by using zebrafish FGF. This new formulation was called modified TESR1 or mTeSR1, and this is the media that STEMCELL Technologies began manufacturing and selling in 2007. So we've now been selling this PSC maintenance media for 12 years. We've learned a lot about making this media over 12 years. A very large proportion of our QC department at STEMCELL in Vancouver is purely focused on screening the raw materials that go into this product, especially the BSA, to make sure that the mTeSR media that you receive from lot to lot to lot every single time has no variability in it. It's very, very difficult to do. So mTeSR is now the most popular PSC maintenance media in the world. It's described in over 2,000 peer-reviewed publications. It's a very good medium. However, as I said, after making it for such a long time, we've started to learn a lot about the media system, the culture system. Okay? And we've seen some opportunities for improvement on this original formulation. So we wanted to share this with you today. So we have just released a brand new product called mTeSR Plus. So mTeSR Plus in its most basic form is a stabilized version of mTeSR1. We have enhanced the buffering capacity of the system, and we've also stabilized a number of the components in the formulation, including FGF2 or BFGF. And this supports cell quality while allowing for alternate feeding schedules. We've enhanced the growth characteristics and the morphology characteristics with mTeSR Plus. We've increased the cloning efficiency with this medium. It's also compatible with all of the protocols that have been developed with mTeSR1, be it gene editing protocols, differentiation protocols, etc. Now, without a doubt, the most common question that we get asked at STEMCELL, or I get asked at STEMCELL anyway, is, do I have to feed my cells every day? Because I don't want to come in on the weekend. Okay? And honestly, the real answer is yes, you do. Because mTeSR1 contains a lot of critical components that degrade very rapidly at 37 degrees. Okay? And if you've got very confluent cultures with a lot of cells in there, these are cultures which are producing a lot of lactic acid, and they're taking a lot of the nutrients out of this media system. Okay? You really do need to be refreshing the medium every day. This is what we wanted to focus on with mTeSR Plus. We wanted to try and get away from that, and we believe that we've done this. And you can now create your own passaging and feeding schedules as long as you follow two rules. This is on the left. If you want to skip 2 days, you perform a double feed. For example, 4 milliliters per well on a 6-well plate. If you want to skip 1 day, you perform a regular feed, 2 mils per well on a 6-well plate. And based on these two rules, you can generate an infinite amount of passaging schedules, feeding schedules. And you can change these as you go. So the key thing that we've done, or one of the key things that we've done, is stabilize BFGF. Okay? We use the same BFGF in mTeSR Plus that we do in mTeSR1. We do not use the thermostable wild type, the thermostable mutant. We use wild type FGF. So native FGF, we've stabilized in mTeSR Plus, and we've done this by the formulation. Here you can see concentration of FGF relative to time 0 degrading rapidly in mTeSR1, and it's down to about 20% of the original concentration after just 1 day. This is why you need to feed every day. Okay. In mTeSR+, concentration remains nice and high after 72 hours at 37 degrees. Now we know that by stabilizing just this one component, that doesn't do everything. It's not going to enable you to do completely flexible schedules however you want. Okay. There is a large amount of evidence that is building on why the pH of the culture system is tremendously important. So a more acidic environment has been shown to lead to growth arrest in pluripotent stem cells, altered differentiation patterns, and increase in the amount of DNA damage in the cells. These papers aren't in the handouts, so please do feel free to take down the references and ask me later if you'd like to read them. So, when I was doing my studies and I did not want to come in on the weekend, I used to come in on a Monday, and this is what my cultures used to look like. They were bright yellow. Okay, so I had really, really acidic cells sitting there in an acid bath all over the weekend. And I knew when I came in on a Monday and I was setting up my experiments for the week, that if I was starting with cells that had been cultured in this over the weekend, they weren't going to be very happy. Right? The variability that you're going to be getting from cells that have been cultured in this medium versus cells that have been cultured in this medium, we know they're going to behave differently. Okay. So with mTeSR+, we've tried to stabilize the pH of the system. And in this experiment, what we did was seed a random number of cells into 6 well plates, and this was single cells, so we could count them. Okay. We then left these cells for 72 hours, so over the whole weekend, and we measured the cell number and the pH when we came back on Monday. Now, the ideal pH range for PSC maintenance is between 7.2 and 7.4. So we want to be within this region here. Now, what you can see with mTeSR1 and a competitor of ours, competitor S, that by the time you get to these very high cell numbers, so this is 3 million cells in one well of a 6-well plate, that's very high, that's very confluent. You're now down to a pH of about 6.8. With mTeSR+, we're maintaining this approximately 7.2, even at these very, very, very high cell numbers. So we're very happy with this change. Colour stays nice and rich, this orangey red colour that we like to see, even after a prolonged period of time at a very, very high cell density. So we actually believe that stabilising the pH is potentially even more important than any stabilisation of any set cytokine that could have been done. Now, as a result of all of these stabilisations, we've gone on to enhance the growth and morphology of these cells. Now, important to note that over the next few slides, all of the data that I'm going to show you has been done using this passaging and feeding schedule, where we passage on a Monday, skip, feed on a Wednesday, skip, and then double feed on a Friday, and don't come in for the rest of the weekend. Okay. So when we applied that protocol to mTeSR1 cells and mTeSR+ cells, you can see that we're getting different morphologies back. So at day 6, the morphology actually looks pretty good in both conditions. But by the time we get to day 7, this is where we start to see a deterioration in the morphology in mTeSR1 cells. So very jagged edges. This phased brightness around the edges, this border here, which is indicative of loose packing of the cells or subsequent differentiation. Now, we do not see this in mTeSR+. We actually get much larger colonies. We're getting completely normal morphology. We actually see better morphology in mTeSR+ with this restricted schedule versus daily feeding with mTeSR1. So again, very happy with this new medium. I won't spend too long on this slide, but just to say that the marker expression Trial 160 and OP4 remained very high and equivalent to mTeSR cultures that have been fed every day. I mentioned that the colonies were larger and getting more cells. So here you can see for 4 different cell lines that were tested, we're seeing an increase in the diameter. The condition that resulted in the highest number of cells was mTeSR plus with daily feeding. Here in orange we have mTeSR plus with restricted feeding, that schedule that I showed you before. And here we have mTeSR1, so much lower, almost half the number of cells at the end. Now, a lot of people think this is great because we want to get as many cells as we can and do more experiments at earlier time points. This actually worried me initially because higher cell numbers, in my mind, meant well, the cells are growing more rapidly. If the cells are dividing faster, is that not a hallmark of cancer? Okay, so that's kind of worrying. So we wanted to look into this and make sure that this was okay. And it's important to note that it's not just cell division time that goes to how many cells we've got in here. It's also the rate of apoptosis of the cells, the cell attachment, is there increased cell attachment at the beginning? And also, is there reduced cell detachment as we go through these 7 days? So I was very happy to report that when we looked at this first one, this rate of cell division, this is the bad one, the division time was identical between mTeSR1 and mTeSR plus. So we are not seeing an increase in the rate of cell division. We are seeing an increase in cell attachment at the beginning and a decrease in the number of cells that are floating off and dying throughout the passage. So in summary, mTeSR plus is a more permissive environment for PSCs. That's why we're getting higher cell numbers. We also went on to validate the pluripotency of these cells, again using this STEMdiff Trilineage differentiation kit, and we're getting very similar results to what I showed you before, this nice patterning of ectoderm, mesoderm, and endoderm markers. So these cells remain pluripotent in a restricted feed state. This was the worrying one. Are they genomically stable if we stop feeding as much? We tested these 2 cell lines. We've actually gone to 20 passages now, not 15. And these were normal with the genetic analysis kit results and GPAF. Now we know that many researchers are genome editing. Okay? We also know that one of the big problems with PSCs is that they do not like sitting down as single cells on their own. Okay? PSCs like friends when they sit down. If we want to screen 100 clones or 200 clones for a genome edit with such a low cloning efficiency, this is actually very difficult, especially if we want to do single cell deposition where we fact sort 1 cell per well into a 96-well plate. Cloning efficiencies with mTeSR and ROCK inhibitor previously were about 1%. So if we want 200 clones, we're going to need 200 plates. Okay, that's a lot of feeding. That's a lot of screening. You know, it's tough when you've got low cloning efficiencies. Now, I'm not going to go through all of this, but we are generating a protocol for genome editing in mTeSR plus. But I did want to focus on this one product. It's a very low-cost supplement called CloneR, and it is there for significantly increasing the cloning efficiency of PSCs. Now, as we mentioned, traditionally, people are using ROCK inhibitor to stick these cells down. And when we do this in mTeSR1, as I mentioned before, we're getting cloning efficiencies of between 1 to 5%. In mTeSR plus, this increases maybe to about 5 to 10%. Still not enough, it's still very low. In CloneR, we're getting cloning efficiencies of up to nearly 30%. Okay. So that means if you want 100 clones to screen, you only need 4 plates. Okay, so this actually makes this whole process a lot more simple. The clones that we're getting back also grow faster in mTeSR plus, which means that these clones establish more rapidly, means you can pick them earlier, usually after about 7 days after your genome edit, and you can start to run your screening process a lot earlier, so it saves a lot of time. Now finally, I'm not going to go through each single differentiation protocol and kit that we have, but what I can say is that we have validated every single kit that we sell, and mTeSR plus cells with restricted feeding do not perform any differently to mTeSR1 cells fed every day. Here's a nice cerebral organoid that we derive using our STEMdiff cerebral organoid kit. For ectoderm, we also generated neural progenitor cells and astrocytes. For mesoderm, here you can see some really nice cardiomyocytes made using our STEMdiff cardiomyocyte differentiation kit. We made hematopoietic progenitor cells. And for endoderm, here you can see our new STEMdiff intestinal organoid kit generating intestinal organoids, definitive endoderm, and pancreatic progenitors. Okay, so that wraps it up, and I just wanted to finish with a take-home message slide. So we know there's a renewed focus on PSC quality with a recent increase in cell therapy applications. We've identified a number of critical cell quality attributes for morphology, genomic integrity, genome marker expression, and the validation of pluripotency. Single-cell passaging is the #1 risk for increasing the takeover of genetic abnormalities in PSC cultures. Genome editing can be enhanced with the clone supplement. And finally, we've optimized the most widely published PSC maintenance system, mTeSR1, to enhance these critical cell quality attributes with mTeSR.